we are ready about the second plenary talk by Karl-Theodor Sturm. So let me explain his career shortly. So he began to study mathematics and physics at the University of Erlangen-Nuremberg, where he got the PhD in 1989 and his habilitation in 1993. So visiting and research positions led him to the universities of Stanford, Zurich, and Bonn, as well as to the MPI. In 1994, he was awarded Heisenberg Fellowship of the DFG. Since 1997, he is a professor of the university at the University of Bonn. Since 2013, he is member of the executive board of the Collaborative Research Center 1060, the mathematics of emergent effects. And then 2011, he is managing director of the Cluster of Excellence Hausdorff Center for Mathematics. His research work is focused on stochastic and geometric analysis, and as well as his pioneering work on synthetic Ricci bound for metric measure space. In 2016, he was awarded an ERC advanced grant for his research project on metric measure space and Ricci curvature analysis, geometric, and probabilistic challenges. So he's going to talk about today optimal transport, heat flow, and Ricci curvature on metric measure space. Please, welcome.
Yeah, thank you very much for the kind introduction. Also, thanks for organizing this wonderful joint conference of Korean and German mathematical societies. It's a great pleasure to be here. I will give a talk on this very fascinating field of metric measure spaces with synthetic Ricci bounds, which started about 10-15 years ago. So the outline of my talk is as follows. I first will give you a short hint why we should be interested in Ricci curvature and why we should study this in the context of metric measure spaces. So actually I will explain Ricci curvature never in classical Riemannian terms. So you never will see any Christoffel symbols or things like that, but only via its consequences for analysis, geometry, or probability. And one of the most fantastic observation was that there is one property which captures all the consequences which Ricci curvature has, essentially all consequences. So in some sense, the idea in the beginning of this development was whenever you take a textbook in Riemannian geometry and find a result depending on Ricci curvature, this should depend on this, what we call curvature dimension condition. This is just one single property of this space. We will study heat flow on metric measure spaces, and finally in the last section we pass to the time-dependent situation where we link this analysis on metric measure spaces with a recent fascinating development of Ricci flows initiated by Hamilton and Perelman. Okay, why should we study these questions in the setting of metric spaces or metric measure spaces? So let me first of all very roughly describe Ricci curvature as the trace of sectional curvature. Even if you are not an expert in geometry, sectional curvature you can measure just by looking on planes and checking whether triangle comparison holds true or Pythagorean equality is correct. And then if you have sectional curvature, Ricci curvature, you have to fix a direction and then you add up the sectional curvatures in all these planes, which have this direction as one of the two spanning directions. So Ricci curvature is a mean value of sectional curvature, so it's a more weak concept, so you can have Ritchie curvature bounds even if there is no sectional curvature bounds. Sectional curvature bounds, they have been studied already in the mid of the last century by the Russian school around Alexandrov, and they developed a synthetic concept of sectional curvature bounds, both a theory for sectional curvature bounded from below and a theory bounded from above. And this is a very perfect self-contained theory which allows to prove many of the results which depends on sectional curvature. Then Gromov observed that the Ritchie curvature, which is the essential assumption in analytic results, that Ritchie curvature has this nice property that families of Riemannian manifolds with Ritchie bounded from below, dimension bounded from above, and diameter bounded, that these families are relatively compact. So whenever you have such families, you can find this convergence, but the limit is not necessarily a manifold. So therefore, Giga-Golding initiated the study of these Ritchie limit spaces, limits of sequences in this family. And in contrast to the sectional curvature theory, where the theory of Alexandrov provided such a framework for studying limits of these objects, in the case of Ritchie curvature, this was unknown for many, many years. So typical examples of these Alexandrov spaces are spaces which you observe if you just take the surface of this lecture room. Yeah, you have points where you have positive curvature infinite, you have points where the curvature is negative infinite, but all this fits into the framework of geodesic spaces and of synthetic Ritchie bounds. And by observation of Lot Villani and myself, more or less independent at the same time, we could find a concept of curvature dimension bound, so which is a synthetic formulation for a lower bound on Ritchie curvature and an upper bound for the dimension, which allows us to prove compactness of families of metric measure space which have this curvature bound, this dimension bound, and which have a bound on the diameter. So this was the analog to the Alexandrov theory together with Gromov's compactness, which in particular applies also to this Alexandrov setting. And this is what I'm going to explain in the sequel. And now let me very briefly explain a little bit why we are interested in Ritchie curvature. Let's say for simplicity, non-negative Ritchie curvature, just to simplify the formulas. This implies that many properties of analysis of probability, in particular of optimal transport, of Brownian motion, of heat flow, of spectral analysis, are more or less the same as for the Euclidean case, as for the Laplacian on Euclidean space, heat kernel on Euclidean space. So more or less the same, of course, means instead of equality, you can only hope for inequality. You have heat kernel comparisons. So the heat kernel can be bounded from below by the Euclidean expression. You have very precise estimates from above and below by this famous Liao estimates. There are sharp gradient estimates. So if you ask yourself, how does the heat kernel improve smoothness of functions, you know that the gradient after time t is bounded by the heat semigroup applied to the gradient. Or you have transport estimates, this W stands for the Kantorowicz-Wasserstein distance. If you start the heat flow in two different locations, you can ask yourself, does this heat flow expand distances or contract? And if it's not expanding, this is an indication that you have non-negative Ritchie curvature. And pathwise, very sensitive formulation of this is in terms of Brownian motion. You can, if you have non-negative Ritchie curvature, you always can start Brownian motions at any given pair of points, such that pathwise the distance between these Brownian motions never increases. And indeed, these properties here, the gradient estimate, the transport estimate, the coupling property of Brownian motions, they are equivalent to non-negative Ritchie curvature. So in some sense, this is what you should have in mind. Don't think of Christoffel symbols, don't think of trace of sectional curvature. Of course, this is also important. But we are more interested in properties which are expressed in terms of probabilistic, analytic, or other geometric quantities. These properties characterize Ritchie curvature, and of course you can try to take any of these properties to give an abstract definition of Ritchie curvature, and indeed it turns out that finally we can take each of them. To begin with, these properties are not so helpful, so we begin with another property. But what turns out is if you want to use geometric concepts to model phenomena in real life, quite often you are interested in a stability of initial data. If you want to model, for instance, financial markets or other effects in such a way that the dependence on the initial point does not really increase the evolution in such a way, then your geometry has to be of non-negative Ritchie curvature. And this is used by people modeling quite different objects. There are various interesting papers now, also in the discrete setting, because these properties also make sense if you replace your smooth space by discrete space. Now you have intuitive idea what should be the right concept. So instead of Brownian motion, you think of random walks and transport properties and so forth. I won't go into these details, but from the very beginning, it's clear there is a way to pass into very different directions. So as I mentioned, we did not take these properties, any of these properties as the starting point. What we have chosen as a starting point, and we means Lot Villani and myself, we have chosen the convexity of a Boltzmann entropy as the defining property. So if we have a metric measure space, which means a metric, complete separable metric on a given space and a locally finite measure, this is what we call metric measure space, then we say that this space has Ritchie curvature bounded from below by K if a Boltzmann entropy, defined with a plus in front, is K convex along geodesics. More technically, we formulate it that way. Whenever you have two measures in your space of probability measures, you can connect them by a geodesic, and this geodesic is defined in the so-called Wasserstein metric, Kantorowicz-Wasserstein metric. I will explain this in a moment. So we should also observe that our datum has distance function and measure, and the measure enters in the definition of a Boltzmann entropy, and the distance function enters in the definition of a Kantorowicz-Wasserstein distance. So this defining property, here it seems that only the Boltzmann entropy appears, but these are geodesics in this metric. So the underlying geometry determines what are so-called Wasserstein geodesics. I will explain a little bit what is this Wasserstein geometry. So this is just a brief reminder of optimal transport in the very elementary setting. So the whole story started with Morsch, who asked, how can we minimize the transport costs in the following sense? If we have two probability measures, we want to find a map which pushes forward the measure mu into the measure nu, and such that the transport cost, which is just the distance between the point where we start and the point where we end up, in the LP norm is minimal. This is one way to define the transport cost. Of course, it's easy to see that in many cases for a given pair of probability measures, there does not exist even one map which does the job. So if this is a discrete measure and this is a continuum, you won't find a measure which maps a discrete measure into a continuum. So in this case, all this transport cost will be infinite. And anyway, it's a very hard problem also from the perspective of analysis to find the optimizer for that. Kantorowicz, independently, more or less, in the beginning of his Morsch problem, formulated another problem which is of similar nature. He did not ask for transport maps, he asked for so-called couplings, which are in our language just measures on the product space which have two measures as marginals. So if you think of measure mu being this measure and measure nu being this, one coupling, for instance, is the product measure. Yeah? If you project it to the axis, you have a measure mu. If you project it to the y-axis, you have a measure nu. And whenever you have such a transport map, the push forward of identity and transport map will give you such a coupling. Of course, this is not really a very clever way to choose this measure if you want to minimize the transport cost. So it turns out that this is a much more smart way. So there are plenty of ways to find such couplings. And it turns out that minimizing this functional means that your measure should be close to the diagonal. And it turns out that actually this measure sits on a very small set. It sits on the graph of a function. And this is the famous result of Notch-Schmidt, Rüschendorf, Radchev, and Brenier, which simply says if the initial distribution is absolutely continuous, then all these problems, Morse, Kantorowicz, and so forth, coincide. So the transport cost in the Morse sense, and in the Kantorowicz sense is the same, and also the minimizers correspond to each other. So there exists a unique optimal coupling, there exists a unique transport map, and this transport map is the gradient of a unique convex function, unique up to a constant. So this explains why the optimal coupling in particular is really the graph of a function. So this is the graph of this function f, which is the minimizer of a Morse problem. And if you go a little bit further, we see that in the Riemannian setting, we can obtain a similar result. Whenever the first of these two probability measures is absolutely continuous, there exists a unique minimizer of a Kantorowicz problem, a unique minimizer of a Morse problem. And this transport map of a Morse problem is just the exponential map of a gradient of some C-convex function. I won't go in details. And what is important now for the interpretation of this optimal transport, if this is your measure mu naught, if you want to transport it to the measure mu1, you end up with this map f, or f1, I call it here, which is the exponential of gradient of phi. But you can plug in a t, which means you go only part of a way from x to y, and you stop in between. So you have a map ft. And if you push forward this measure mu naught with a map ft, which is obtained just by going for geodesic only part of a way, then you obtain a measure mu t, and this measure mu t is the measure on the geodesic in the Wasserstein space. And again, this geodesic is unique. So if you have a measure which is absolutely continuous and another measure mu1, you always have a unique f1, you have a unique geodesic in Wasserstein space, and this geodesic in Wasserstein space really means you transport the mass, let's say, halfway in order to obtain the midpoint. So this is a rough idea of this optimal transport, which links the geometry of the underlying space with the geometry of a space of probability measures. And this is now what we use to formulate Ritchie curvature bounds. We have an underlying geometry where this gradient and exponential map comes from, and then we go to the geometry of a space of probability measures. So let me switch back now to the, so this was the Riemannian case. Let me switch back now to the metric measures setting. Let's emphasize again, this is the L2 Wasserstein distance. You try to minimize the distance square among all measures which have marginals mu1 and mu0 and mu1. And if your underlying space is complete separable, then the space of probability measure with this measure is complete separable. And if the underlying space is compact, or if it's a length space, or if it's an Alexandrov space of non-negative curvature, then the same is true for the space of probability measures. It's not true if you replace the zero here by a constant. It's also wrong if you have a less equal zero. So far, the definition, once again, the definition of a curvature dimension condition. As I mentioned, our definition, Lot Villani and my definition of non-negative Ritchie curvature is saying that the entropy is K-convex. Why is this meaningful? Why should we believe that this is a good definition? If you think of a round sphere which has positive curvature, if you transport the uniform distribution from a small ball into another small ball, then by the positive curvature of his space, the space of midpoints is larger than the space of his endpoints. So there is more room to spread out. If there is more room to spread out, then the Boltzmann entropy is smaller. So the entropy in between is smaller than the entropy at the endpoints. This is exactly the convexity of a Boltzmann entropy, because there is more space here. And this is the basic idea behind all these definitions. Let me also mention very briefly, this is really the powerful formulation, the classical convexity with a correction term for the K convexity. There is a rewriting of this if you already know that the function is semi-convex. Instead of this classical formulation, you also could say convexity means that the slope along the geodesic is increasing. This would be geodesic. The slope at the left-hand side is less than the slope at the right-hand point. K-convexity means that the increase of its slope is not only non-negative, but it's larger than this quadratic correction term. And with this formulation, we can add another correction term, which is just the difference of his entropy functions at the endpoints, and this is then the so-called curvature dimension condition Kn, where a second parameter shows up, which is just a real number, positive real number, but this is interpreted as an abstract dimension bound. It's not really the Hausdorff dimension of anything. It's at the beginning just a number. But what turns out is if we specify this, if we, for instance, look on the curvature dimension condition with non-negative curvature and dimension bounded from above, this condition can be reformulated as the convexity of a Rényi entropy. Instead of a Boltzmann entropy with rho log rho, now we have rho to a power less than 1. Actually, it's 1 minus 1 over n. And it turns out that this Rényi entropy is convex if and only if we have non-negative curvature and dimension less than n. This Rényi entropy has a quite nice property. For instance, if you calculate the Rényi entropy of a uniform distribution of a set of volume, on a set A of volume MA, then this is just the nth root of a volume. So the nth root of a volume in physical terms is of the order of a length. So this is a way to describe that certain mean values of lengths are concave. And remember that Alexandrov geometry says the space has non-negative sectional curvature if whenever you start two geodesics at the same point, then the distance between alpha t and beta t is a concave function. So this is what you always observe if you have positive curvature. If you walk on the sphere, the distance function is a concave function, if and only if you have non-negative sectional curvature. Now, Ricci curvature means that you have non-negative Ricci curvature if and only if the nth root of a volume element is a concave function. This is the intuitive message of this definition. But of course, this is not really very useful as a definition. It's also very vaguely as formulated here. But here in this picture also it's an attempt to say not each length here is really a concave function, but in the mean value this is concave. So it's exactly what is here formulated in this abstract setting. Okay, what can we say about this definition? For Riemannian manifolds, the curvature dimension condition is equivalent to the lower Ricci curvature bound and the upper bound on the dimension, and it includes weighted Riemannian spaces, Ricci limit spaces in the sense of Giger-Colding, Alexandrov spaces, Finsler spaces. If you agree that also certain notions can be interpreted as quasi-distances and so on, then also the Wiener space is incorporated. It would be a space with curvature bound 1 and dimension infinity, and there are also configuration spaces and many other constructions, suspensions and so forth, warp products, cones, limits, and so forth. So there is a huge machinery to create new examples out of given one. The most important stability results for this definition are that we have a tensorization property. So if you take a product of certain spaces which have curvature, Ricci curvature bound from below, K from below, then also the product has the same curvature bound. We have a local to global property, which is very important, and it's absolutely non-trivial here, because we have a priori, we have a global definition of curvature by studying convexity of entropy really on the whole space, but there's a local to global. If we check this in small neighborhoods of any point, then we can get it globally. Which is, of course, an essential property of a curvature. Whenever you would like to define curvature, you would have, you want to see that this has a local to global. This is one of the strong statements in geometry, that from local observations you can conclude global statements. And it's stable under convergence. This was the most important property, because this is, of course, not the case in the Riemannian setting. In the Kromov's precompactness theorem, if you have precompactness, okay, you don't know whether there exists a limit. But here in this space of metric measure spaces, this is now the crucial point. The space of all metric measure space which have this curvature bound, this dimension bound, and in addition a diameter bound, this is compact. So whenever you have a sequence of these spaces, there exists a limit. Each Gromov-Hausdorff limit in the Cheeger-Colding sense is an element of this space. And there is one other important result which is more technical for the moment, but of course also very important for us. There is another definition introduced by Ambrosio Chili-Savary, which combines this curvature dimension condition with a linearity of a heat equation. I will come to the heat equation in a minute. You also could rephrase this, that this means that the tangent spaces are Hilbert spaces and not Banach spaces. So you want to exclude Finsler-like structures. So tangent space being Hilbert also would be correct if you agree what is your definition of tangent space. And now what are the consequences of curvature dimension condition? As I mentioned, just go to a textbook in Riemannian geometry, don't look at the proof, try to find the proof by yourself, and then you can more or less obtain each of these results. The first important result is Bishop-Gromov about volume growth of spheres. And this is in some sense a quite easy result in this setting. The picture is very easy. You have a transport problem from a central point to a big sphere. And on the way in between, you stop at the small sphere. And convexity means at the small sphere, you have more space. And this is exactly what you put in quantitative terms, and this is the sharp formula from Riemannian geometry, and this follows out of our definition. So the volume of a small sphere compared to the volume of a large sphere is bounded from below by this ratio. A consequence of that, indeed, is immediately the Bonny-Myers diameter bound. So if you have curvature n-1, let's say, and where n is the dimension bound, then the diameter is less than pi. So this is the famous Bonny-Myers diameter bound, which follows actually immediately from our Bishop-Gromov comparison result. There's another important estimate, the spectral gap or Poincaré inequality, again, as in the Riemannian case. And there are also a number of related results in the case where n is infinite. So this still makes sense. It simply means that lambda 1 is larger than k. These properties don't make sense anymore. But a replacement, for instance, of this Bishop-Gromov are concentration of measure results. There is the Talancroix inequality and the Log-Sobolev inequality, which are the corresponding infinite dimensional counterparts to, for instance, Sobolev inequality. For metric measure space with linear heat flow, we have a rich analysis on these spaces. And most importantly, we have a Bochner inequality, we have a Laplace comparison, and the Liao estimate. So Liao estimates, in some sense, if you have a Bochner inequality, you can try to run this machinery. So these are very precise estimates on heat kernels. This is the Laplace comparison for the distance function or for the square of a distance function, and you reprove the results known from the Euclidean case. What is now very interesting, and I want to stress Fies results a little bit more. There is the splitting theorem and maximal diameter and Opperter's theorem. So let me briefly say what splitting theorem means. If you have non-negative Ricci curvature, and if there is a geodesic of infinite length in each direction, then your space splits into a real line and a space orthogonal to it, and you can write it as a product, not only in a measure value sense, but really as a metric measure space. It splits into real line and a space which morally is one-dimensional less than the original space. An analog to that is the maximal diameter theorem, proven by Ketterer. If you have curvature positive bound and dimension bound, let's say curvature is n-1, then we know that the diameter bound is pi. Then the maximal diameter theorem says if there is a pair of points which has distance pi, then this space has to be a suspension. So you take these 2 points of maximal distance, call them South Pole and North Pole, and then there is a new space, which is your equator, and everything is just a suspension of an equator between these 2 points. So you really reduce, and the equator then is again a metric measure space which has a curvature dimension bound. And a very nice application of this is the following result proven by Erba and myself just recently. And I like it very much because it's extremely easy to formulate. If you have curvature dimension bound with curvature larger than n-1, and if this integral of a double integral of a cos of a distance function integrated against 2 variables is non-positive, then the only choice for this is that n is an integer, which up here was just a parameter, a real parameter, and the space is the round n-dimensional sphere. The proof of this is indeed rather easy, because Bishop Gromov tells us that under these assumptions, this quantity is non-negative, and the distance is maximal pi. But if it wants to be 0, we conclude that from any point, we have to find an antipodal point which has distance pi. So we can make the Ketterer result and find the equator, the basis of our suspension. And this basis, and when we can rewrite with a law of cosines, the distance of a space x in terms of a distance on the base space. And it turns out the base space has the same property. So we can iterate that. And we can iterate that as often as we want, and sooner or later we end up with an n which is less than 2. If n is less than 2, the only choice for this is just a circle, and then we are done. And there is no space for a real number. But this is a very impressive rigidity result, because you start just with a metric measure space with some convexity properties and integral quantity which should be minimal, and then you have identified the round sphere. The most important result in this theory, proven just this year, is the fact that these RCD spaces, so the spaces which have curvature dimension condition with finite dimension and with linear heat flow, that these spaces have constant dimension of their tangent spaces. So first of all, these tangent spaces are Euclidean tangent spaces of a given dimension. This we knew from the work by Mondino and Neighbor already since some years, but at that time it was still possible that the space is covered by a countable number of charts, each of these charts having a different dimension. But now it's clear that there is only one dimension, one integer, of course, some integer number smaller than this n. And this is a result which was known for Alexandrov spaces since a long time, but actually also for Cheeger-Colding limits. Analogous result was only proven in the last decade. So this is a very important result here. Now I mentioned already that there is a heat flow, and we used already properties of a heat flow quite often. What is the definition of a heat equation on such a space? So one important observation, I called it here A, is that a priori there are two possible definitions of a heat equation. The more standard definition is to define the heat equation as the gradient flow of the energy in L2 space. You have to give a meaning to energy, and but this is possible. Actually, there are various approaches. All of them lead to the same result. You can start with a minimal weak upper gradient following the Finnish school of analysis, or you simply take the local Lipschitz constant, squared and integrated, and make this functional lower semi-continuous, just taking the relaxation in L2 space. Both will lead to the same energy function. And by work of Otto, Jordan, Kinderlehrer, we know that in many cases the heat equation is also the gradient flow of a Boltzmann entropy. And indeed, this is not only true in Riemannian case or in particular in Euclidean case, but this is true for every metric measure space whenever this Boltzmann entropy is semi-convex. And semi-convexity is our definition of curvature bound. Yeah? So our lower Ricci curvature bound simply means that the Boltzmann entropy is semi-convex. And whenever we have this curvature condition, then the heat equation, now considered in this picture, regarded or considered as a flow of measures, is the same as this flow of functions, where of course function and measures are related to each other by the fact that this function is the density of this measure. Yeah? And in particular, this means the heat flow immediately produces density wherever you start it. If you start with a Dirac or whatever, at positive time, the heat equation has a density. And the next important result, which links these two approaches, the Eulerian and the Lagrangian approach to heat equation, is now a characterization of Ricci curvature, of lower bound of a Ricci curvature. We have seen this as our definition of curvature bound, the K-convexity of entropy. There is a more classical definition by Bakri and Emery, already some 30 years ago. They introduced the so-called gamma-2 condition. In their notation, this simply means that gamma-2 is larger than k times gamma-1. More abstractly or more explicitly, it means that we have a Bochner inequality. Yeah? It's a condition which controls the commutation of a Laplacian and the gradient of a Laplacian versus Laplacian of a gradient. And this Bochner inequality is the analytic version. From the Bochner inequality, you can deduce the gradient estimate, at least with exponent 2, immediately just by integrating the Bochner inequality along the heat flow, or from here, this you obtain the Bochner just by differentiating the gradient estimate at time 0. These two properties also seem to be very related, at least for Q equal 2. Indeed, if you have a K-convex functional in a reasonable space, you would expect that the gradient flow is K-contractive. And this is exactly what is written here. This is intuitively clear, but technically, of course, not so easy. And the equivalence between those properties is the so-called Covata duality, which holds true in a very general setting, that gradient estimates correspond to transport estimates with a dual exponent. The famous, well-known version of this is for Q equal 1 and P infinity. This is the Kantorowicz-Rubinstein characterization of L1 Wasserstein distance in terms of Lipschitz functions. Now there is a work in progress. There are various extensions. For instance, we try to formulate this now with variable Ricci bound. So we have to replace this gradient estimate. And it turns out that the appropriate replacement of this gradient estimate, where we have e to the minus kt times the heat semigroup, is a Schrödinger semigroup, which more explicitly can be formulated with a Feynman-Katz formula as follows. The gradient of PTU is the expectation of a gradient of u times e to the minus k bs ds, where the Ricci curvature bound is integrated along the paths of a Brownian motion. There's an even more fascinating extension which also incorporates Neumann boundary conditions. And also in this setting of metric measure spaces, we are able to give a meaning to the local time of a boundary and to the curvature of a boundary. And in addition to the curvature, which is integrated up in a domain, we also have a contribution from the boundary, which could be regarded as a measure-valued Ricci curvature sitting on the boundary. So this is, and it could have both signs, so this is also interesting for convex domains, but it's even more interesting for non-convex domains, where this is really a negative measure, and without this contribution, the estimate could not be true. And the third extension, which I want to mention, are the time-dependent spaces. So we think of families of metric measure spaces modeled on the same space, but with one parameter family of distance functions and measures. We assume that for each t, this space is a nice space in our sense, and that we have some regular dependence of the distance and the measure dependent on t. Then we have a heat kernel, as we expect in nice parabolic situations, a kernel which depends on S and t, the starting and the endpoint, and x and y, such that if we integrate functions against the heat kernel, we get solutions to the heat equation, and if you integrate measures in the second variable, then we get solutions to the dual heat equation. I will do not go that much in detail. It turns out that also in this time-dependent setting, now the heat equation is a gradient flow for entropy, but now you have really to distinguish. The heat equation goes forward in time. If this is my time direction, heat equation on function goes in forward time direction. This is the gradient flow of energy. And now the dual heat flow goes backward in time. It acts on measures, and acting on measures, it is the gradient flow of a Boltzmann entropy. So in the time-independent case, we simply could switch between these pictures, just saying functions are the densities of the measures. This is no longer true here. We have two different pictures. Functions evolve forward in time, measures evolve backward in time. Evolution of measures is the gradient flow of entropy. Evolution of functions is the gradient flow of energy. Gradient flow is here also should be regarded with care, because you intuitively you try to go in the direction of a steepest descent if you want to make your next step. But in the process of making the next step, both the geometry will change and the functional. So even if you believe that this is the best way to minimize your functional, if you do first step, the functional might change. So it's not really true that the energy decays along this flow or that the entropy decays, but nevertheless, this is the heat equation and this is the dual heat equation which comes out of this construction. The construction really means it's the attempt to make a decay of these functionals, even if this does not decay in the time-dependent case. And we have a similar equivalence as we had in the static case. So we have a characterization in terms of dynamic convexity of a Boltzmann entropy. I won't have time to go in these details. We have a contraction property in the Wasserstein distance. Now in this dual picture, we have two measures which flow backward in time and do not increase the distance. We have a picture in the sense of gradient flows. We have functions going forward in time, do not increase their gradients. And the abstract formulation of this is you simply differentiate at time 0. You end up with a Bochner inequality. And the most comprehensive way to formulate this in the Baku-Emery language means gamma 2 is larger than time derivative of gamma 1. And there is also a nice property in between, namely that you can characterize this stuff by Brownian motions, which can be coupled in such a way, Brownian motions running backward in time, such they do not increase distances. All these properties are equivalent to the following property in the Riemannian case, namely Ricci curvature plus time derivative of metric tensor is non-negative. So this is the famous, if there would be an equality, this would be the famous Ricci flow equation of Hamilton, Perelman, and many others. So what we study here are inequalities. So if these are, instead of Ricci flat spaces, we study spaces of non-negative Ricci curvature. And here, instead of Ricci flows, we study so-called super Ricci flows. So in the remaining case, any of these properties is equivalent to that. Most easily, you might see this from this last property. And let me finally point out what is ongoing work and what are challenges. I already indicated with these boundary effects that one of the challenges is to incorporate measure-valued Ricci bounds. This really plays an important role if we want to study boundary effects for non-convex domains, if we want to incorporate branching, for instance, on graphs. Of course, Ricci curvature is always infinite, but it's not arbitrarily infinite. There's a negative Dirac at each branch point. So it also can be quantitatively taken into account, and the same with a non-convex boundary domain. If you have a Neumann boundary condition on a non-convex domain, of course Ricci curvature is unbounded from below because it's measure valid. There's a negative, there's a measure negative of a surface measure, for instance. Challenging topic is screwing of metric measure spaces. We are trying to get that. There is partial work on upper Ricci bounds, and what are challenges for the next future, and hopefully other people also will contribute to that. First of all, of course, Ricci flows and heat flow on general spaces. Parallel transport, stochastic parallel transport, this is still a missing concept, very challenging. And there are two very explicit conjectures. If you have a metric measure space which has a dimension bound 2 and a Ricci curvature bound, then we expect that this should be an Alexandrov space with the same curvature bound in K as Alexandrov curvature bound, and with M being the volume, or a one-dimensional space. I avoid it now for case of one-dimensional space. It's unclear. Many people try to prove this. Even more challenging project is to prove that in dimension 3, every metric measure space which has synthetic Ricci curvature bound is a Giga-Colding limit. Or to disprove this. Yeah, also in this case, in any of these cases, also disproof would be a great thing. Okay, thank you for your attention.
Thank you for the nice talk. So some questions, comments? Professor O?
So you talked about the super Ricci flow. I don't quite understand what it means. Did you mean this is the super solution for Ricci flow equation?
Yes.
So this super...
Could I have my slides?
Yeah, I guess the last part of your talks.
Here. This here. This is super Ricci flow. Super solution to Ricci flow equation.
So in what sense? In the viscosity sense, or?
No, let's say in the, so this is a result for metric measure spaces.
Yes.
And if our metric measure space is a smooth family of Riemannian manifolds, then this is just a smooth solution of this super Ricci flow.
Okay. I missed the Riemannian.
I was doing a little bit fast at the end.
Any other questions? Yeah.
In the time-dependent setting, can you also deal with discontinuous? Here you suppose that you have a derivative in time.
Yeah.
More general.
So we have various partial results which allow to incorporate, let's say, a countable number of singularities just by as an approximation result. This we know, but what we would like to know, or what I would like to know, is really a general result, because in the static case now we know whenever we have a metric measure space, we know there is a unique definition of a heat equation. And with the space-time setting, of course, it's much more sophisticated. Yeah? We can cover a lot of cases which have singularities. Yeah? One possible situation is we have in time there is a countable number of singularities which can be approximated such that the heat equation is continuous either in L2 or in Wasserstein sense. So we have both tools. We can apply heat equation or gradient flow over entropy. So this allows us for a lot of flexibility. But still this look more like model cases and not like a general theory. It covers all the cases which are studied in Ricci flow in Riemannian geometry. Yeah? But from this abstract point of view, still something is missing.
One other comments or questions? So I have one. So is there any special things for the NPC space for your talks?
Now, NPC spaces will enter the picture. I was tempted to formulate this as a challenge here, to study harmonic maps from RCD spaces to NPC. This is really the most natural setting. And indeed, this is also one of the challenges right now to prove Lipschitz continuity. If you start from a metric measure space and go into a metric space, for the target space, the right assumption should be lower Ricci bound. For the target space, upper sectional curvature mounts. And it should be true that we have Lipschitz continuity. People try hard, but at the moment, nobody could prove it. Hölder continuity is clear. It's also true if domain space is an Alexandrov space with this Ricci curvature bounds. So if it has a little bit additional structure. But the general case is still unclear. But this is, and people also try to study the differential of maps. Not only proving the Lipschitz continuity, but more general to understand the energy density of maps.
Okay, we finish. Let's thank to the Karl-Theodor Sturm.